What I plan to do today is little more on data types before we get into core of n-dimensional arrays. One thing I have to cover it, which I have not done so far. We will do that, and then Endianness I want to talk about how that impacts the array that you create. Normally it should not, but there are some occasions wherein you may have to have some awareness about it. And then one dot product example we will see today. Okay. Now we saw quite a lot of all the types we have seen already, what each of them do and how to create an array of this type. All of that we have seen now. One thing is pending is about the object. Okay. There is a background noise. Okay. Now this is little unique compared to all of the rest of the types. Okay. The difference is when you want to create an n-dimensional array of NumPy, the main restriction is that the arrays elements should be of same type. Okay, same type. The reason they have put that condition is that they don't want to test on every iteration accessing every element is a type different from whatever it was earlier. So which Python does it in list, it can have any number of different data types can be there, but it will verify that and then try to access it accordingly because it is maintaining the references to that. Now here, if it's not a references here, actual contents are being stored, so they don't want to have additional information for identifying what type of variable is in each element. So it's all like a C array or a Python array wherein it's a contiguous memory and we have a same type of array elements being formed. Now what is the difference between normal data types and the object type? Now this object type is a reference to an object. Now since it is a reference, it's an address. So as long as it is referring to an object, we can now the normal Python object has the information about what type of the object it is, we know which class it belongs to, and all the details are there in the as a part of the object memory. So anyway, it has to be a dereferencing because it has to access the address and then get to the object that is being stored. So even in the NumPy array, we can have any object being arranged as an object type array. So as long as it's an object type, it doesn't matter whether it is a class X or class Y or class Z, we can have any object of any class and it will be able to resolve it while it is accessing them. So let us see an example of this in the class today. I hope this is clear to you. Now let me start off with, before I start, I wanted to touch on one more thing about platform. There is a module called platform. Now suppose you are interested in knowing what type of architecture is being the Python is running on. We can do that using a type. Okay, I will not type it, it takes more time, so let us I will take it out and then that is better rather than saving time. What we want to learn is what is it about. So there is a platform architecture and there is it looks like a function, but if you see the type here, this is a tuple. Okay, this is actually a tuple, has two elements. Okay, one, both of them are strings. It passes on two values, two strings, whether it's a 32-bit processor or 64-bit processor, and whether it is running on Linux flavor or a Windows flavor, on which OS platform it is running on. So this gives you the information. So suppose if you want to find out what is the platform you are running on, you can use this module. So I am intentionally doing it because it is going to be helpful for you to understand about the object references that we are going to see. Now let me not type everything. So let me take a class definition. Now I want to create a object of different classes. Now you know that this is the initialization, and str this dunder function is to, if you are giving the object of this class, it will print this value. So it will be helpful to know what type of object it is. So if you are having normally I suggest that if you are writing any classes, default have this function in your class, so that if somebody passes an object, we will immediately know what type of class it belongs to. And if you have something like a member function, you can print that value also, which I have done here. This will help you to know what is I'm sorry, it will not work. Okay, I have to give slash. Okay, oh, I don't know. Okay, let me not do this. I put a tab here. Okay, what is the problem even now? One second. Okay, now we will take few more classes. Now I created objects of different types, classes. I want to create an array of this type. So now before that, let me start with one object, and then I will explain you what I am doing. Okay, now what we are doing is we want to create a type of object and passing a object reference that I have already created an object, and it passes back that it is actually storing it in the NumPy type. So what you are getting is a NumPy type object, and we have a reference passed to that, and we are creating a num type of object, object type of NumPy array. Not even array, it's a one single element. Now what is the type? We can see that it gives you type as a class main x, because main function is what is being called, and we are having the value. I'm just printing it. Print when I'm passing the object reference, it prints you the value, because we have defined the str dunder function for the class. So now if I create an array of this object, and then if I initialize it with different types, does it allow? So that's what we are trying to see. That's the uniqueness of the object type in an ND array, n-dimensional array. Here we are creating 3 element of object type, an object array of NumPy. Now individual element I am initializing it with different objects. So this is the only array which is of type object in NumPy that can have references to different types, different objects. Okay, it's a type is object type, but still we can refer to different objects, whereas in all other cases we can have only the integer type or a float type, the same type of array you can create. Now what is the use of this particular feature that they have provided? I can think of something, but you guys can always try to use it in places where you want to create an NumPy array of object type. Maybe need not be object, it can be a structured type. Okay, you can have a structured type of one can be object type, and then other elements can also be there. This can be a built into this, and then maybe based on that element or the operation being to be done, we can call different algorithms. Okay, if suppose you want to have a time sensitive algorithms as well as something which is taking more time but accuracy is more. Maybe we can have different classes referring to different implementations of objects within the class, and based on the configuration or based on the type of the image or type of the data that you have, you can call different algorithms on that. So if you are aware of that, there is a possibility that you can actually build an array of NumPy which is having ability to call different classes. You can use it when you come across that kind of implementation. So I would like you to think about it, what you like to use and where you want to use. But once you know that this is possible, you can think of using it. Okay, so that's why I am showing this. Now let me show you what is the content of this array that it talks about. Now, okay, now what we have done, we have created an array of object type 3 element. We have initialized it with 3 different objects. Now what do you expect this item size to be? Item size is a pointer to a object. Now what is the pointer size? Now that's why I printed this platform, and it showed that it is a 64-bit which is running. That means even the Python version, let me show the Python version, that is also a 64-bit version. Okay, I think I already shown. Is a 64-bit Python version is what is running on a 64-bit processor. So the pointer will be of 8 bytes. Okay, 64-bit width. And what is the elements? Number of elements 3 it should be, and then total size will be 3 into 8 anyway. So you had object reference type width is 8 bytes. Okay, that keep in mind. Now can I access them individually? Yes, you can, and that we can see here. So I'm trying to access individual element. Now what is happening is we have stored to 3 different objects. So I wanted to print 3 different names, and we get object X, Y, Z is what is coming. Okay, so I hope this is clear to you that we can access it. We can have a different classes or objects which can be there in a array. Now let us go back. I hope there are no questions here. Okay, fine. So this is clear. We have covered all the types now. Okay, including the void and string. String we covered in the lab. Now the major important thing also that you should remember is the behavior of NumPy and Python integer types are different. And the NumPy integers, even if it overflows, it doesn't give you any warning. It just undetected. It goes undetected. So you need to be careful about it. Unlike Python, the size of NumPy int is fixed size. Okay, chosen by dtype, whether short or integer or int 64 or float 32, that will be different. Whereas integer in Python can grow as per the requirement, as per the value that you are storing it in an integer. It can keep on growing. That there is no upper limit on how much value you can store in an integer in Python, whereas that is not the case with the NumPy. So now let us try to run a code. Now this is the power function 100 to the power 8. Using int 64 we will use, it will print actual value. If you use a 32-bit value, then it will not be able to print the correct value. Okay, so let us see that behavior so that you understand what is happening there. I am avoiding typing so that you only get the crux of what is required. Now what we are doing is power 100 to the power 8, and if you use 64, that means the value. Okay, well, let me tell you one more thing. When we have this kind of 3 inputs to this power, it is trying to compute up something to the power of something, x to the power y. But how does it know how much of bytes it has to accommodate for storing the result back into the after the computation is done. So it cannot go by the value that you are giving here, because these two both values are only a byte wide. It is possible to hold them in a byte unless you tell the type what you want the final result to be. No, it cannot default find out. Otherwise, what it will do is it will find the maximum of whatever is there. That value it will choose if you don't give the d type. Now we are giving specifically int64, then it will force the result to be on of type int64. Now I can also force it to the 32-bit value. Then 100 to the power 8 will not be fit into this 32-bit wide integer. So it will not give any error, but you will get a wrong result when you run it. So if you are having int64, you get the complete value, whereas if you are only allocating int32, you will not be having the actual result, and it doesn't give you any warning or error or exception, nothing. So you have to keep this in mind when you are writing NumPy related algorithms or values, intermediate results as well as the final result. It might overflow. That you need to be aware of. Now, what if I do something like this? I will tell you. Suppose 100 to the power 100, if I do 100 to the power 100. Can I do it with only int 64? It's not possible. If I have float 64, what happens is the computation is performed in a floating point arithmetic. So what it does is, based on the parameters, whatever is the maximum precision or maximum type that you have mentioned, it picks up that to perform the job. So here, because you have put float 64, even though these are all integer values, it will perform a floating point arithmetic and then give the result back in floating point. So if you run this, you will get a proper value. Okay, 10 to the power 200, 100 to the power 100. Okay, you get this result properly. Okay, so whereas here it is overflown, that value whatever you try to get it is a 0. Okay, so that is what is happening. Remember this kind of intricacies when you are dealing with numbers. Okay, now let me, what is that? And I have already explained it in the lab. You can have a min and max, you can find out. And I don't know whether you guys have paid attention to this. I'm sorry. This is in the last class, Monday class. IInfo is for integer type of family of variables, data types, and this is for floating type, floating point type of variables. You can get the information about what is the minimum and maximum of particular data type. So there may be many. Just I am introducing you to some of them. It's only a tip of iceberg, because you should know that there are these features available, which you should accordingly use it when you are writing a code, and if you are stuck anywhere. Okay, I hope this is clear. Now let us come to Endianness. Now let me explain something here. Most of the time the Endianness is not understood properly. Let me try to explain that what I mean by Endianness. This is memory. This CPU. CPU has a register which is bit 0 to bit 31. Assume that it is a 32-bit CPU. Bit 0 to bit 31 register is there. Let me call it as a R0 register. Now it has got address bus, and data bus is always shown like both direction. Address is always one direction, because CPU is putting the address onto the memory and then trying to get read from the memory or write into the memory. Now Endianness comes into play when a CPU is working with a DRAM. This is a DRAM, okay, and trying to write the values into the memory. Now always the LS byte of your values will be in the lower part of the register, and then MS byte will be here. It will be always correct. Okay, now let me call this as a byte 0, byte 1, byte 2 and byte 3. This is the 4 values of 32-bit value. Now when it is writing into the memory, it has got two ways of storing this value. Either I am flashing, suppose I am giving an address 100. Now what happens? always the memory is addressed in terms of bytes. So address 100 is going to hold some value, 101 is going to hold something, 2 and 3. Now the value what you have, sorry, I put okay, only this much. Okay, 3. Now the values have to be stored in the 4 consecutive locations. When this value is written into the memory, it has got a flexibility to either write it into this order or in this order. Okay, sorry, 3 2 1 0. So 3. Okay, B0 1 2 3. It can either store it from the LS byte order or MS byte order. This is called little endian and this is called big endian. So when the CPU is running and it is configured on power on reset, it can be configured to be a big endian machine or a little endian machine. If it is an ARM processor, if it is on the boot up, it decides, and then it can access it in this way. Now, suppose in a multi-core processor, when the CPU is also interfaced with another CPU, okay, and assume that this is a little endian machine, this CPU is a big endian machine. If you are interfacing with the two different CPUs and they have a common memory which is shared between these two, suppose. Now assume that this CPU is a little endian and it is writing into the memory. This is a shared memory. Okay. Now this CPU is operating in big endian mode, but it is configurable. Assume that it is configurable. Either it can be configured as a big endian or little endian. Whereas this is a little endian machine. Assume that it is only little endian. Now it is going to write into the memory in a little endian format, and then if it is trying to exchange some information between these two in a multiprocessor core, then what happens is this CPU, when it is accessing it, it needs to know what type of NDNS is followed while writing into the memory. If it doesn't know and if it is operating in big endian mode, what it will only say that okay, integer value is there in this address. This CPU may inform this CPU. Now in that address, whatever is stored, it would have stored in the little endian format, and this guy assumes it a big endian format. The values what it reads will be swapped out. All of them will be wrong. So you can configure it during that time. Only when you are accessing this memory, configure it as a big endian and access it. And then if it is transferring from here to here, maybe it has to write it in a, bring it to the register and then write it back into the other mode. So only between the memory access to the CPU, the NDNS comes. Okay, that you have to understand. Now, why are we worried about this NDNS in the NumPy array? Because NumPy array is a byte array. We are storing it as a contiguous memory. Whatever data is stored need to be following some NDNS, because any integers that you have will be following some NDNS and then it will be stored. Now the machine, the CPU, what is running, it may be running a Python in the top, but NumPy is a C programming interface. So it is actually running a C code to access your arrays, and it is running on the CPU. So you have to know what is the NDNS of this CPU, so that the data is written. You know that this is the way it is written into the memory. Now what if you are trying to send this particular raw data, what you read from the array, on a network, suppose. Okay, on a network you want to put it as a IP packet. In that data area is there, you want to write it in some way and then send it out as a packets. You want to send it out as a packet. If you are forming a network driver or something you are writing, then it should be in a big endian mode. So whatever may be the mode of this CPU, it should send it across as a big endian mode. So we need to worry about the NDNS when you are communicating with the either as a shared memory or through network. Then we need to worry about it, because we are going to access the raw data from here, and then directly maybe you may be copying from memory to memory copy. In that case, you need to be worried about that. Okay, but if you are doing it only in the Python level, it is taken care of by after the CPU brings it to the register, it is being accessed by the Python code. So it will not be having any NDNS problem. So that's why portability is there at a higher level languages. But when you are handling at the byte level, you need to worry about the NDNS. Now there is a NDNS byte order. You can read about this, more about this. There is a method which is given as a byte order, which gives you one of these values. Means you can say that it is following the native byte order. That means whatever is the CPU it is running on, whatever is the native byte order of this CPU, that is what is being followed. If suppose if you want to know a particular data type, what byte order it is stored, you can use this function to find out the endianness. Okay, are not applicable. Now, when is the byte order does not play a role at all? I'll tell you. Suppose if you have a data which is a short data, short integer, and then you have a byte 0 and byte 1, then when more than one byte is there, then the endianness comes into play, because you can store it in the address either B0 first and B1 next, or you can store it in B1 first and B0 next. So endianness comes only when the data is more than a byte. But if it is a only single character or a int 8, suppose, NDNS doesn't come, because byte is stored as a byte and you are accessing it, and it doesn't matter what NDNS is. So if you are trying to find out the byte order of int 8, you will get not applicable. Whereas if you use this value which is more than a byte length, you may get a native. Okay, native means whatever is the CPU's byte order is being followed, because it has to be same as what is CPU being following it. Okay, so I hope the explanation is clear. Now let us try to run some code on our machine, because I am running the Intel CPU. You will know what type of thing to get now. So let us just write it now and see. Okay, now suppose I have I2 means 2 byte of integer. Okay, now before I run it for 2, let me run it on 1 byte. What happens? Okay, 1 byte, it says this is a symbol, which means that it is not applicable. Why? A single byte doesn't matter, whether you cannot store it in two different ways. It is only 1 byte, so it doesn't give you any NDNS business. Now suppose if I am storing a 2 byte value of integer. Okay, now what happens? That data type, what is the byte order it is going to store? Now I am trying to get a byte order and then size of the DT also. DT is 2 bytes and it is equal. Equal means what? Native. So still it doesn't give you whether I am running it on a little endian machine or a big endian machine, I don't know. But whatever may be the machine I am running on, it says that it is following the native CPU's byte order. It doesn't give you the actual type, whether it's a little endian or big endian. Now that you can make out by using a function. Let me introduce. Okay, sys is there already. So if you want to know that, you can say sys byte order. System byte order is little. So that is one way of doing it. Now other intelligent way of using only the NumPy thing is, I thought I will show you that. Before that, let me show you. Okay, this I already shown. Okay, let me copy it and show you this. Okay. Oops. Okay, now if I say uint c, unsigned integer c, it's a more than a byte value, so I will get the byte order which is native. If I say u byte, it will give me not applicable. Okay, and then if I give system byte order, it will give you little. So that's what will happen. It is first one is native. This is, it doesn't matter. I'm storing a byte, so there is no NDNS business there. And system byte order says it is little. Now how do I use something that NumPy gives? How do I use it? So let me show you this particular thing. It might be helpful to you in some other occasion. So I thought I will show you this so that you know that there exists something. Now let me explain. We are having uint c type of data type, Okay, I am creating an object of this unc type, okay, using the dtype class, and then I want to use the new function which is called new byte order. Let me tell you what is it. Control I. Okay, new byte order, it returns a new data type with a different byte order. Okay, it changes the type of the byte order in which that is going to be interpreted will be different. Okay, it swaps. S means swap the d type from current to the opposite endianness. Now what has happened is, remember one thing. Okay, let me explain why it is I am calling it as a non-native here, because whatever is the current byte order which is being followed is the native byte order. Okay, that's what we saw here also. It is also native. Okay, now you are intentionally swapping it. So the new byte order of this type, the type what you are getting will be non-native. That means it is different from what is being actually running on with the CPU. So this is a non-native type. Now, if I do a byte order of non-native, okay, it is not the same as what you are getting right now, what you are running on. Okay, so that non-native byte order will come here. Okay, now let me run it and show you what is happening. Let us these are the output. Let us compare. Now print type int non-native is a d type, some d type, but it is storing the values of u and c in a non-native way. That means the byte order which is different from the current byte order which is the Python interpreter is running on, and I want to know what is its byte order. If I say byte order, it will have to say something about the type. Now greater than means big endian. Okay, that's what is the it says greater than means big endian, less than is little endian. We are forcing it to tell by changing the native order to the non-native order, and then we are printing it. Okay, this is the one way of forcibly making this function to tell you what is the byte order you are running on. So it gives you is a non-native byte order is this. Now what happens is, if you do it twice, suppose if you are calling this swap twice, it will come back to the native byte order. Okay, so I am doing it twice on that and then storing it here and then trying to find out the byte order. Then I will get the actual by a little endianness. You will get it here. Okay, otherwise normally it will give you native or not compatible. But if you try to do this swapping business, you will be able to derive the byte order of the machine that you are running on. So I hope this is clear to you. The intent is to expose you to this underneath what is happening, so that when occasion comes or if you encounter some issues, you will know which one to worry about. Okay, what to worry about. Okay, that's all. So I have nothing else on data type. So we will stop here on data type. Now we will get into something which you might have already done in your data science courses, a simple dot product. So it's an algebraic operation on which two equal length vectors are multiplied. Okay, so it's called inner product or a scalar value. So when you do dot product, I'm sure you are aware that you are multiplying matrix multiplication, you are doing on a transpose of matrix, something like this. So B prime is a transpose and we multiply it. Now what happens is the individual elements are getting multiplied and added. So what you get out of this is a scalar value, which is 1 by 5 by 5 into 5 by 1. It will be a single scalar value what you get. Now we will just create one small array using NumPy and then try to perform this multiplication. So it is of contiguous memory, all that you know. So what I'm going to do is a small code wherein I want to create an array of type D. Now how do you know what type it is? Now this is the character code that for each of the types is defined, and D is for double. So we are creating an array of length whatever 1000 into the 10 power 6 elements, and the values what you are assigning them in individual thing is increasing number 0 to 9999. Okay, that's what you are filling it up. And then B array, again it is being done in a floating double operation. So whatever integer value you are getting is going to be converted into double and then stored in the array. So you are going to have a huge array of values which are ranging from 0 to something in double format. And then we want to perform a dot product using normal floating Python code, which is for I length of a, one of the length. Okay, anyway you need to have the same length, otherwise it will give error, because a dot product if you are performing you need to have of the same dimension. So here we are doing it as a individual element, we are multiplying and adding it. And what if you do it in NumPy dot is a function. You give two matrices, it will give you. So you perform the same operation. Now if you compare the time, you will see the much better improvement. And this already I have explained in the lab, so we don't have to spend time on this. So let us just run the code. I think I can directly show you the code rather than typing it, because you might have been already familiar with this, so it's nothing new. And then yesterday also you wrote the code, so it's nothing big. So same thing I'm doing. Okay, I'm creating a double type, that is only maybe new to you if you are not familiar. And then I'm performing the individual element wise multiplication and addition to get a scalar value, and I am timing it. Okay, one more thing I wanted to tell you based on what I saw yesterday. Especially when you are trying to measure the time taken by some operation, start time and end time. Okay, you need to be careful on what you put it into this timing block, because you are measuring some particular operation. So do not mix multiple operations here which you are not actually measuring the performance. Now one example is, suppose if you are doing a dot product, okay, example here np dot a and b. Now if I time it, let me say print small p. If I say this np dot a comma b, if I put this into this, am I measuring the time properly or not? T1 and T2, we are not. The reason is, we are not only measuring the time taken for this multiplication, we are also measuring the time taken for this print to actually print the value that you are generated. So sometimes it may be a small thing, but it depends on the implementation, because print, as you guys are already implementing the printf now, it is actually accessing multiple things here, libraries, print libraries, and then sometimes what happens is the complete printing is happening, or it will be written into a buffer. Okay, what happens is, when you are trying to print, you are calling putchar or something. Now what happens is, the putchar is going to be doing a processing of this thing. Okay, suppose if the result is of a big into the 64 value, and then you have a wide 64-bit wide data, then each of those 64-bit value needs to be converted into ASCII, and then they need to be written into a buffer. Okay, all the ASCII of that buffer, and then only the print comes out. Okay, sometimes a print may even wait till that thing is output, because it is an interpreter. Okay, remember, our Python is an interpreter, so print will not come out until it gets printed on the screen. That's what we normally see, because it is a line by line execution. So what happens is, it also includes the time taken for printing the value on the screen, which is much more time involved, because it is not only putting it in the buffer. Okay, that buffer value is to be taken out by the display driver, and then it should be displayed on the screen. So what you are measuring is not only the computation of this, you are also measuring the time taken for printing it on the screen. And if this value happens to be long, and it is a longer string, that means it will be taking more time. So what you measure time will not be accurate. So what you do is, in this cases, just assign it into some variable a equal to np dot dot. Only this much you do, and then print you can do it outside, so that you measure only the computation which is being done. Okay, this is a very important point you should remember when you are trying to measure the performance of things, because underneath what is happening you should be clear. Okay, print is not a simple thing. It may, especially on Python, it will take a lot of time, because it has to print it on the screen, then only it will go to the next line. So end time will be taken here. If you put a print here, it will be printing it, and then only it will compute the end time. So it will be much longer than the computation time of the dot product. Okay, I hope this is clear to you. Now let me just print this. This is nothing very great. So computed value is something big, and time taken for this is only 0, and this is this much. Now I am not doing an ns. Maybe I can do ns and then see whether it is compared. Okay, that you know very well how to do it, so I don't need to do that. So this is all about a dot product. Okay, now I am sure you guys are aware of basic data types of ND array. So let me show you something before we stop it today. And then we will spend some more time tomorrow, maybe more into arrays. This is a single axis array, multiple elements. Okay. And then it is 2 axis, 2 rows. Always this is one more thing is, each array is stored in the row major fashion, because you know that ND array is a byte contiguous byte, so it has to store all the values in some order. So it follows row or major. For obvious reason is that NumPy is implemented in C, and C follows row major, so it has to be. So somebody asks you, why should Python NumPy uses row major? You can give the reason that because NumPy is implemented in C, and C follows the row major. So it fills the row first in the memory, and then it fills the remaining rows. So that's how it is stored in the memory. And shape gives you what is the number of rows and column. Okay, so let me run it. It's very simple. 2 rows and 3 column, and dimension is 2. Okay, because there are 2 elements in this array. Okay, 2 row, even though it is a row, 2 n dimension is how many? I'm sorry, 2 dimension is different from 2 element, because I have only 1 row, and the another dimension is the second row we are introduced it. So there are 2 dimension to this, 2 axis to it, axis 0 and axis 1, and that's why you are saying NDMS dimension is 2. And then I'm sure you must be familiar with this range. A range is being used for the array type of for the NumPy, it is a range. So you can create a range of values and create an array. Okay, and you can create a different type of float and then complex. Okay, that very simple data types in arrays what you can generate. Okay, so and one more thing is, this is complex 128. As I mentioned, it includes a 64-bit value for one real and 64-bit value for imaginary, and it defaults it if you don't mention any d type, it assumes that it's a double. Okay, whatever values are double. Since I have given it complex is always taken as a double, and even though you are given integer values, it is taking it as a double and storing it. That's why you see the data type of this array is complex 128. Okay, I think that's what I had today, exactly on time.